In this video, we're going to take a look at ligand binding to proteins. This is a reversible process where we're setting up a chemical equilibrium of molecules A and B coming together to form this AB complex. The molecule that binds to a protein is referred to as a ligand. This is typically a small molecule, although it can be a protein. And the region where this ligand is going to bind the protein is known as the binding site. So if we look at our example below, our ligand is this blue triangle. On our protein, we have this spot, which is our binding site, which is complementary to the ligand. That's where our ligand will be bound to the protein. This is going to be through non-covalent interactions largely. So your hydrogen bonding interactions, ionic interactions, van der Waals interactions, to have this complex. And this is going to allow the interaction to be transient and reversible. There is a rate constant associated with the two molecules coming together to form the complex. That's your Ka, or association rate constant. Similarly, there's going to be a rate constant associated with that complex coming apart to give you back your free protein and free ligand. That is your dissociation rate constant, or lowercase Kd. And with this, this on and off reactions will occur until we reach equilibrium, where the rate of our association rate constant, it becomes equal to the rate of the dissociation rate constant. So this does set up an equilibrium constant. The one for Ka is shown there. We're going to be more interested in the inverse of that, the Kd, or dissociation constant. So if we look at our association binding constant Ka, it has units that are inverse molarity, which is kind of unusual to kind of get your head around. As I said, we'll be focused on the dissociation constant. You know, this is the large capital K D. So the units for this will be molarity for the most part. We will do some examples where we're looking at gas, so it'll be somewhat different, but that's okay. We can relate those association and dissociation rate constants to the free energy, or delta G values. You know, this is to see whether or not they're favorable or spontaneous, and to what extent. In this class, we won't be doing those calculations. What we're going to have you focus on is having a firm understanding of what the magnitude or values of these KDs mean. So for something to have strong binding, when we use that term strong binding, we're talking about something that has a ligand that has high affinity for our protein we're working with. These values are typically in the low nanomolar range, or maybe even lower than that. So the actual numerical values are small or low. In contrast with weak binding, these are low affinity interactions, and our Kd values are going to be at the higher end. So we're seeing here micromolar or better, so 10 micromolar or higher. If we look at some examples here of known binding interactions, at the left-hand side, we can see our biotin-avidin. This is one of the strongest known interactions. You can see that our Kd value for that is approximately 10 to the negative 15th molar. That's a very small number. So that's high affinity. As we increase the value of the Kd, going from that 1 times 10 to the minus 15 to a Kd of about, we'll say 1 times 10 to the minus 3 molar. That's a very large value, which means we have low affinity. So those are going to be inversely related. Something with high affinity has a low Kd. Something with low affinity has a high Kd value. You can see that our enzyme substrate interactions are usually in the micromolar to millimolar range. That's because your substrates are designed to, be recognized by the enzyme, be converted into product, and then released. So if your product wasn't released, it wouldn't be a very good enzyme. So we'll take a look at what we're going to be working with, looking at our reversible binding of a ligand to our protein. So we're going to be analyzing the amount of the ligand that's bound. So there's a couple different ways we'll see this. One of the ways is looking at the fraction of occupied binding sites. So for our purposes, we said that we're going to be focused on the KD values, not KA values. Under these experiments, what we're assuming is that our value of the ligand that we're measuring is comparable to the total ligand. And what we're going to do graphically is plot our ligand concentration on the x-axis. And we can either plot this as the fraction of occupancy or some other, we'll have a couple different terms, but largely this value is going to be the fraction that's of the binding sites that are occupied. So our KD value is going to be that concentration of ligand that gives us half of our binding sites occupied. It's very, very difficult to achieve these high concentrations to ever get 100% binding. So that's why we're using the 50% mark. So to determine your KD value, let's see if we just put little marks here, 1, 2, 3, 4, 5. So in this example, if you want to determine your KD value from a graph, you would locate the portion on the y-axis where you get 50% of your binding sites occupied, go over to the curve, and then drop down and see what your ligand concentration was. So with that rough estimate here, our KD in this example will be equal to approximately, we'll just give this units of molar, or we'll do nanomolar. Our KD would be not 1 nanomolar in this example. So looking at another example here, we just have y on our y-axis, so that's going to be our fraction bound. So if we wanted to estimate our KD value for this ligand, we would go and find where we have 50% binding, our occupancy of the binding sites, drop down to the x-axis, and that's at about roughly 0.1 molar concentration. So our KD is approximately 0.1 molar in that example. All right, we can do a couple more here. Now we're looking at the binding of ligand A. So we have one ligand and it's binding to 2 different proteins, X and Y. So in the first part of this example, we want to determine the dissociation constant, or KD, for each protein. So we'll do that. So for X, we're going to come over at the 50%. We nicely have that dashed line there. Drop down to our X-axis. So our protein X has a KD of ligand A of approximately 2 micromolar. All right, we'll do the same thing for Y. So since the dashed line is already there for us, we're going to drop that down to the X-axis. So for protein Y, our KD value is approximately 6 micromolar. Okay, so that's part 1. So which protein has the greater affinity? Remember we said greater affinity meant lower KD value. So our greater affinity is going to be protein X. And if you think about it, we need less of ligand A to get our 50% binding sites occupied than we need of protein Y. So X has a higher affinity for that ligand. We'll take a look at another example. So in class we'll be talking about oxygen binding to the proteins hemoglobin and myoglobin. So again, here's a curve where we're looking at our fractional saturation on the y-axis. Since oxygen is a gas, instead of having molarity, we're going to use partial oxygen pressures. But the way we look at our affinity or determine the affinity is the same. We're going to start by finding we want to know what concentration gives us 50% binding to our protein. Myoglobin, you can see, is pretty hard to determine. So that's a very small number. In contrast, if we go across, so that's our 50% line, and drop down for hemoglobin, it is going to achieve a 50% saturation at 25, a PO2 of 25 torr. So here what we'd say is clearly myoglobin has the higher affinity for oxygen because we need much less oxygen to get 50% of those sites bound. The other way you can see these is whatever, if your curve is to the left, a shift to the left, if we say hemoglobin is our standard, if you shift to the left, that's a higher affinity. Shifting to the right is a lower affinity. One thing you might notice with this graph here is that the curves for myoglobin and hemoglobin look different. We see that our myoglobin has a hyperbolic curve shape to it, so that's a hyperbolic curve, whereas the hemoglobin has that sigmoidal S-shaped binding curve. The reason for those differences is due to cooperativity. So this is something that's going to apply to proteins that have multiple binding sites that are capable of interacting with one another. Usually you see this in multimeric proteins such as hemoglobin. These are examples of, this is an example of allosteric regulation. So allosteric proteins are those in which binding of a ligand to one site affects the binding properties of a different site on the same protein. And so we can either have a situation where it's homotropic, meaning the normal ligand of the protein is the allosteric regulator, and we'll look at that today. We can also, this could also be heterotropic, meaning a different ligand affects the binding of the normal ligand. So we'll talk some about that as well. This process we're going to talk about, or phenomenon, is called cooperativity. So with positive cooperativity, the first binding event increases the affinity for the remaining sites, and this is recognized by those sigmoidal binding curves. This is what we have with oxygen binding to hemoglobin. Negative cooperativity would mean that your binding event at the first site reduced the affinity at the remaining sites. We're going to focus on this positive cooperativity today, where our first binding event increases our affinity for hemoglobin. So if we look back at these curves now, our myoglobin, which has the black line, the myoglobin protein itself is a monomer, and it just contains a single binding site, oxygen. We'll do oxygen binding site. That does not have any cooperativity, so it has that hyperbolic shape to it. In contrast, our hemoglobin protein is a tetrameric protein. It has multiple oxygen binding sites to it, and it has this sigmoidal shape in the pink, or S-shaped, as it does have, or it does exhibit, cooperativity. So you should be able to distinguish between a protein that has cooperativity and one that doesn't based on the shape of their KD curves. So knowing that, you can still use the same basic premise for determining which protein has a higher affinity for a given ligand, or which ligand has a higher affinity for a protein. In this example, we're going to stick with using the same ligand, in this case oxygen, and we want to figure out or determine which protein has the higher affinity for that oxygen. In this example, the curves are representing fetal hemoglobin, the dashed line, and adult hemoglobin, the solid line. We'll talk about what BPG is during lecture. That's an additional ligand. But we want to just look at the curves and use the information that we know to determine which protein has a higher affinity for oxygen. And again, to do that, what we want to do is find out what ligand concentration, so what PO2 concentration is going to give us 50% occupancy of our binding sites. So again, we take that, let's draw it straight across. That's our 50% line. We're going to drop down for fetal hemoglobin, where it crosses, drop down for the adult. And what we can see, given that the fetal hemoglobin curve is shifted to the left, must be the opposite on this video, I'll do that for the left. Since that shifted left, it has a higher affinity, so you can see we need, our KD essentially would be less than the 2 PO2 kilopascals for binding to the fetal hemoglobin. We're at a value of almost 4 for the adult hemoglobin. So our fetal hemoglobin has a higher affinity for oxygen. You'd expect that since the maternal hemoglobin needs to transfer oxygen to the fetus. So that would be something we'd expect. Well, that is going to wrap up looking at our protein ligand interactions.